Okay, I've got an initial value problem up on the board here, and we're going to try to solve it using power series. Okay. So the directions are two parts. First, we're going to guess the Maclaurin series. Just a reminder, this means it's the Taylor series centered at 0. So T naught, the point where I'm centering things, is 0. That's going to mean that I'm going to have just powers of T in my series. It also means that the coefficients are all calculated based on the function value and the derivative values at 0. That's kind of nice because my initial condition gives me the function value at 0. That actually tells me that a sub 0, the constant term, is going to be 2. Okay. We're asked to describe a sub n, the coefficient in front of t to the n, recursively. That just means that we're describing it in terms of its predecessors. And we'll see how that plays out as we work this through. Okay. Then the second part, once we've done that, we're asked to find P4 of t. That just means the fourth Maclaurin polynomial. Now, that may or may not be a polynomial of degree 4. Okay? Most of the time it is. But if the coefficient in front of t to the fourth happens to be 0, we would still call it the fourth Maclaurin polynomial. It might be the same as the third Maclaurin polynomial, but we're going to go up to and including the t to the fourth term. Again, I like to use this notation because it's nice and concise. Okay? The book tends to just say find the series up to degree 4. So they would say, find our series up to and including the t to the fourth term. Any of those ways are correct ways of phrasing things. You want to be familiar with all of them so that the directions don't confuse you. Okay, so let's see how this plays out. So I'm guessing that y of t is the sum as n goes from 0 to infinity, a sub n, t to the n. Now, if this is the Maclaurin series, I know there's a formula for what a sub n is. It's the nth derivative at 0 divided by n factorial. But it's not helpful for me to write it that way because I don't have a formula for this, so I can't calculate its derivatives. So it's simpler to just say a sub n, that's the nth coefficient. And generally when I'm working with these things, I find it simpler to write it out term by term. So that's going to be a naught plus a1t plus a2t squared plus a3t cubed plus a4t to the fourth plus a5t to the fifth plus dot, dot, dot. Now I'm hoping that's enough terms for me to notice a general pattern so that I can describe what's happening overall. You know that for the second part, we were asked to find the fourth degree polynomial. So to stop here, I did not, however, stop there here, because I know that the t to the fifth term, when I take the derivative, is going to contribute some to the t to the fourths. Okay. So I wrote down a little more than I'm expecting to ultimately solve for. I'm hoping this is enough for me to notice the overall pattern, and if it's not, I'll add on some extra terms. Okay. I do know that a naught is 2. I'm not going to plug that in yet. I'm going to wait till I'm ready to solve for all of the coefficients. Okay. All right, so now I'm going to start working with my differential equation. The left-hand side is just dy by dt. And I'm going to just write that out term by term. So the derivative of a constant is just 0, but I'm going to get a1 plus here I'll get 2a2t, plus here I'll get 3a3t squared, plus 4a4t cubed, plus 5a5t to the fourth, plus, plus, plus. And I can pretty much see what's going to happen. If I wanted the t to the 100th term of the derivative, it would be 99 a sub 99 times, I'm sorry, it would be 101 a sub 101 times t to the 100th. Okay, so I'm noticing the pattern there for the derivative. Okay. Now the right-hand side, that was t squared times y plus 1. I'm going to write that out below here, and I'm just going to line up like terms. Okay. So if I look at t squared y, that means I'm multiplying t squared by each one of these terms. So t squared times a naught, that's going to give me some t squareds. So of a naught times t squared. Now I'm lining that up with my other t squareds, not because I'm going to be adding them, because I'm not adding the left and right hand sides, but because that way they're in the same place. I'm ultimately going to be setting these things equal to each other. Okay. T squared times a1t is going to give me a1 times t cubed. Plus, now I multiply t squared by the next term, that's going to give me a2 t to the fourth. Okay. And so for the t squared y, I can see whatever power of t I'm getting, which are the powers that start at 2 and go higher, the coefficient is just a with a subscript that's 2 less than the power. Okay. Then I had plus 1. So that's going to be my constant term there. Okay, so now I want to try to start solving for things. Notice the a sub 0 has actually, oh no, it hasn't completely dropped out. Dropped out of the derivative, but it still shows up here. I actually know that a sub 0 is 2 because that was my initial condition. Okay. Now, looking at my constant terms here, if the left-hand side equals the right-hand side, those constant terms have to be equal. So I know that a1 has to equal 1. Okay, we'll write that in. Okay. I know that the linear terms have to be the same. Here I have 2a2 copies of t. Here I have none. So 2a2 would have to equal 0. Well, that's going to tell me that a2 is equal to 0. Okay. Now, if I look at the t squareds, what I'm going to get there is that 3a sub 3 has to equal a sub 0. Okay. So that now is going to describe a3 in terms of a previous coefficient. Okay. All right. And I could actually solve for that and say that since I know that a naught is 2, a3 would be 2/3. But I'm looking for an overall pattern right now, so I'm going to leave it like that. Okay. Because this is the first time where I'm describing a coefficient in terms of its predecessors, and I want to be able to do that consistently. If I look at the t cubes, what I'm going to get is 4a sub 4 is equal to a sub 1. Okay. If I look at the t to the fourths, what I'm going to get is 5a sub 5 equals a2. Okay. So this is looking kind of nice. Okay. I am definitely noticing a pattern here. I could solve for a3 and say a3 is a naught divided by 3. I could solve for a4 and say a4 is a1 divided by 4. I could solve for a5 and say a5 is a2 divided by 5. In general, it looks to me like if n is bigger than or equal to 3, I can say that a sub n is going to be a sub n minus 3 divided by n. Okay. So notice here, if I'm looking for a3, 3 minus 3 would be 0. If I'm looking for a4, 4 minus 3 would be 1. If I'm looking for a5, 5 minus 3 would be 2. Okay. So this is now describing the nth coefficient in terms of its predecessors. Happens to be describing it in terms of the coefficient that's 3 terms back. Okay. So I couldn't do that for a0, a1, and a2 because those don't have a term that's 3 terms back. Now, as long as I'm confident that this pattern is going to continue, I'm good to go. And I am confident that this pattern is going to continue because I definitely noticed a consistent pattern in the derivative and a consistent pattern in 1 plus t squared y. Okay. So, for my answer now to part 1, I can say y of t is the sum as n goes from 0 to infinity of a sub n t to the n, where a naught is 2, a1 is 1, a2 is 0, if n is bigger than or equal to 3, a sub n is a sub n minus 3 divided by n. So I've now described all of those coefficients. Excellent. Okay. So now I also wanted to find p sub 4. So part 2, p sub 4 of t is going to equal 2 plus t plus 0t squared plus some t cubes plus some t to the fourths. So now I do need to figure out what exactly is a sub 3. A sub 3 is going to be a0 divided by 3. That's going to be 2/3. So I can fill that in right there. Then I need to find a4, my coefficient for t to the fourth. And let's see, that's going to be a1 divided by 4. a1 was 1, so that's going to be 1/4. Okay. So I've described the entire series, and I've also found that series up to and including the fourth term, otherwise known as the fourth Maclaurin polynomial.